So we'll talk about bilevel optimization today. It is kind of like an optimization problem with a specific structure. And then we will use some of the theory we have developed before to solve bilevel optimization problem. So first of all, what's the motivation of bilevel optimization? So you will see that in the next few slides, we will give you a few practical applications in the real world where we kind of have a hierarchical decision-making structure. In some of the decision-making problem, a leader or a top-level decision maker will solve an optimization problem while anticipating that a lower-level decision maker or the follower will respond optimally to the leader's decision. Okay. So the leader aims to optimize their objective, taking into account the optimal response from the follower. So if this is too abstract there, don't worry about that. We will give you some concrete real-world applications. So some of you might have studied something called game theory before, right? So essentially, there is a very important class of games called Stackelberg game, which is essentially the leader-follower game. It was developed by someone named Stackelberg. So in this type of Stackelberg game, the leader moves first, right? So the leader makes a decision, then the followers have to respond. And the followers will react optimally to the leader's decision. Okay, so mathematically, this problem can be formulated as follows, right? So let's suppose the leader's decisions are x sub L and the follower's decision are denoted x sub F. Right? So when the leader makes their decision, they are optimizing a given function, f sub L, right? So you can think about this is the so-called utility function of the leader, right? Or the leader is trying to optimize their gain. And then, but the leader has to take into account that the follower, after seeing the leader's decision, will react optimally to the leader's decision. Okay? So the follower's problem is denoted as max of x sub F. Okay? So the follower will, after seeing this XL, will optimize their own utility function f sub F. Right? But when the leader makes their decision, they have to take into account that the XF, the follower's decision, is the optimal response after seeing the leader's decision. Okay, so we will come back to this generic framework later on. Right, so here in a bilevel problem, basically the leader is solving a problem where they are maximizing a given utility function f sub L subject to the constraint such that the follower's decision has to be optimal with respect to the follower's objective. Okay, so this might sound very abstract. So let's give a very concrete real-world application, then we come back to this abstract formulation again. Okay. Yeah, so let's think about a particular application called extended market. So in a market, let's say if a vendor wants to sell a given product, you can think about that the price of this market, the market price of this product is related to the total quantity of the product in the market, right? So as you know, if you produce a lot of this product, the market price of this product is going to decrease. So here, let's assume we have two vendors in this market where the total quantity they produce is capital Q, where the leader produces QL, the follower produces QF. Right? So we can assume the leader is like a dominant company, right? Which first take their decision, then the follower will observe how much the leader produce and take their follow-up decision. Right? So the market price of this product would be A minus B times Q. Right? So A is a given constant, B is a constant. As you can see, as a quantity increase, the price of this product will decrease. Right? But the total quantity in the market will be the sum of the quantity produced by the leader and the follower, right? Okay, so then we can talk about the profit by the leader and the follower. So first of all, we know that the leader's profit would be the price. So this is the price, right? A minus B times the total production is the price of this given product. And QL is a quantity produced by the leader. So those are the money that the leader makes from selling the product, right? And then in order to produce a product, let's assume the leader has to pay like a marginal price in producing a given quantity of the product, right? So this equation would be the total profit made by the leader, right? Okay. And similarly, let's calculate what will be the follower's profit, right? So the follower's profit again would be the price of this product times the quantity produced by the follower minus the marginal cost of producing the product times the quantity of the product produced by the follower. Right? So these two are the marginal cost. Okay. So is the calculation of the profit clear? Okay. So as you can see, there are some games going on here, right? Both of the players should be very strategic in how much they play, right? So if you assume the leader makes the decision first, the leader has to anticipate that the follower will respond optimally to maximize their profit, right? And then the price is dependent on both the quantity produced by the leader and the follower. Right? So this is not a so trivial problem to decide what are the optimal quantities to produce. Okay, so in Stackover game, we assume there is a decision sequence where the leader will make the first move of producing QL. So we don't know what would be the optimal QL the leader should produce, right? But we will calculate that based on this Stackover game. So the leader first makes QL, and then the follower observes QL, and then decides how much they are going to make, right? So based on the leader's production quantity, the follower will make the optimal decision after observing the leader's production quantity. Okay. So this is a Stackover game. So it is like a hierarchical decision-making structure, right? There is another thing perhaps you guys have heard in game theory is so-called Nash equilibrium. Right? Maybe even if you haven't heard about it, maybe you have watched some movies. Right? There is an Oscar movie about the Nash equilibrium and so forth. So that is different than a Stackover game. Right? So in a Nash equilibrium, there is no decision hierarchy. Right? You just assume all the players make decisions simultaneously. Okay. So in Stackover game, there is like a leader-follower type of structure. Okay. Yeah. So let's do some very quick analysis here on what is the sort of the optimal QL and QF here. So let's first consider the follower's best response function. Right? What do I mean by that? Right? So no matter how much the leader produces, right, then the follower will respond optimally to the leader's production curve. Okay, so let's take a closer look at what is a follower's best response to a leader's decision. So recall that, this is a follower's profit, right? And no matter how much the leader produces, which is QL, right? Then the follower will respond optimally to the QL. And it is very to see that, this is a concave function, like a quadratic function in terms of QF, right? You have a minus QF squared term here, right? So we do know how to find the maximum of a, negative quadratic function, right? Just take derivative, set it to 0, right? So let's take derivative of pi f with respect to partial derivative with respect to QF and set it to 0, right? So then we get this so-called best response function, right? So the best response function is saying that after the follower C, the leader produces quantity QL, this number or this function is the best response with respect to the leader's quantity, production quantity, right? Okay. So the follower's problem has a closed form solution with respect to Q sub L, right? Then let's take a look at the leader's optimization problem. So as I said before, when the leader optimizes their production, they have to be aware that the follower will respond in an optimal way to their production level. Right? So then when a leader optimizes their production quantity, it has to take into account this best response function. Right? So let's plug in this best response function here. Okay. So now we can substitute this best response function into the profit of the leader here. Right? So recall that in the original formulation, we have the profit is a function of both the production quantity of the leader and the production quantity of the follower, right? But since when the leader is making the decision, they have to make sure that the follower's quantity is always the optimal quantity, right? So you can just plug in this function. So the trick here is that after you plug in the optimal response function, then this profit is only a function of the leader's production quantity. Right? So you are substituting the optimal response now. Then you can decide what will be the leader's optimal production, right? Because you already take into account that the follower is going to react in a rational way to your production level. Okay, so you can just quickly check. This is also a very well-behaved function. You can just set the derivative to 0 and solve for the optimal production for the leader, right? Okay, I'm not going to the details of those calculations, but you get the high-level idea, right? So now we get the optimal production of the leader. Then you can plug in this optimal response function to get the optimal production of the follower, right, given QL. Okay, so this just to give you some idea of how a bilevel optimization problem works, right? For this particular application, you can use very simple tricks to solve this to optimality, right? So the leader is anticipating that the follower is reacting optimally, so you plug in the optimal response function to the leader's problem, then you take derivative to get the optimal leader's decision. Okay. So now let's see any questions here for this toy problem. Yes.
How is it different from the two-stage stochastic programming?
Yeah. So that's a very good question. So in two-stage stochastic programming, you assume there is only one single agent, right? For example, the leader is making decisions in two stage, and the objective is well aligned. But here there are two players. Their objective are not well aligned, right? So the leader's profit and the follower's profit are different. In two stage, you assume, for example, a single player is making decisions in two stage, and they are optimizing their expected cost in the second stage plus the first stage cost. Okay. Yeah. Any other questions here? Yeah, so now let's look at a slightly non-trivial example. You will see this in the real world all the time. So this is called the toll setting problem. So the leader of this problem are some toll setting agencies, right? So if you travel over highways, you know that the tolls has already been set by some toll setting agency, right? So this problem is trying to tell you how those agencies set the tolls for each highway, right? So the leader are the toll setting agency. They are going to set the tolls for traveling on each edge of this graph. So let's assume all the travelers are travel from this this starting point to the destination here, and they are for this particular toy problem, there are two routes to travel from O to D, right? So the AB is one route, the CD is one route. So if you travel through these two routes, the cost can be different, right? So let's assume those gamma variables, so gamma A, gamma B, so the gamma variables are the cost without the tolls. Okay. So for example, those costs can be your travel time plus some fuel costs, right? So here I'm talking about the costs in general, right? So of course there are two things related to cost. One is how much time we will need to travel from here to here, and the other thing can be the cost related to your gas and so forth. Yeah. So those are the costs without the tolls, right? And then the toll setting agency will set a toll for each edge in this graph, right? So let's assume in this case the toll are denoted in green here. So we will see, when you set the tolls differently, how the travelers will travel, right? So let's see, if you assume we set the toll to be 2 and 2, and then here it's 2 and 2 as well, right? So in that case, let's calculate the total cost of traveling through these two routes, right? So if you travel through A, then the cost would be 12, right? So if you add these two numbers up, the base cost plus the toll. And then if you travel through edge B, then the total cost is 7 and so forth. You can calculate this as 10 and 4. No, this is 6. Okay, yeah. So now if you add those numbers up, if you travel through AB, then the total cost is, if you add those up, it would be 19, right? And then if you add those C and D up, the total cost would be 16. So if you are a traveler, let's say whenever you guys go to a place, you will look at your Google map, right? Go to a place and then how much time it is, and then plus the tolls, right? So you will always account for the base cost, which will be the travel time, plus the toll you will pay to decide which route you are going to take. Right? So here, as you can see, the tolls are the same, right? So the tolls for AB and CD are exactly the same. And then in that case, of course, the traveler will choose the route that gives you the least total cost, right? So you will choose to travel through C and D. And on the other hand, if you make this route more expensive and this route a little bit cheaper, which is usually the case, right? If you have a shortcut, usually the toll is higher, right? If you, let's say, for example, you travel from here to Chicago, there's a tollway, right? And that saves you maybe like 10 minutes or so, right? Or you pay like a couple more dollars, right? So here, as you can see, if the toll setting agency set the toll to be 4 and 4 and 1 and 1, then you will perhaps choose the route AB, since in total you are going to have a less cost than travel through CD. Okay. So what is the problem here is the toll agency is trying to decide how to set the tolls on those edges such that they can maximize their profit. Right? When the toll agency set their tolls, they have to use the assumption that the travelers will respond optimally to their tolls. Right? So the traveler will always pick the route that gives them the least total cost. Right? That will be the base cost plus the toll. Right? So as you can see, there are some trade-off for the toll setting agency. If they set the tolls too high, then all the travelers will all travel through the cheaper routes, right? Although it may take more time. But if they set the toll too low, then they are not taking advantage of the travelers who wants to save travel time. Okay, so this is kind of a leader-follower game, right? The leader are the toll setting agencies. They want to set the tolls that maximize their total revenue, and the traveler, of course, they are going to take the shortest path, right? The shortest path in the sense of cost. Okay, so let's formulate this problem. Yeah, so this is just a detailed description of what I just said. So let's formulate this as a bilevel optimization problem. Okay, so let's first define some parameters and sets. As I said, the gamma ij are the base travel cost excluding the tolls, right? If you travel from node I to node j, this base cost essentially characterize the travel time, the fuel cost, and so forth, right? And then there is a demand, or the number of travelers seeking to travel from the origin to the destination. And we have the set of edges, set of nodes, and set of path from origin to destination, right? So in the previous case, we only have 2 paths, right? Okay, so now after the tolls are set, the travelers will decide how they are going to choose the path. So we use this variable xp to denote the number of travelers choosing each path, okay? And then Tij are the variables by the toll setting agencies, right? The leader first need to decide the tolls on each of the edge ij, okay? Yeah. So now what is a leader's problem? The leader is trying to maximize the revenue on all the edges, right? So here we will sum over all the edges. So the toll on edge ij is Tij. Tij is a variable here. Okay, so let's write it down as Ti is a variable here. And then these xp variable are the variables related to the follower, right? So after the tolls are set, the follower will respond optimally by choosing the path, right? So here's the number of travelers choosing path P, right? So if this edge ij is part of path P, then you will do xp times Tij. So this is kind of all the revenue collected by the toll setting agency after the traveler respond optimally to the tolls. Okay, yeah. So what are the constraints here? Of course, the tolls are non-negative. You never make money by traveling through an edge. And the additional constraints, you can include some constraints like the maximum tolls or some regulations to certain roads and areas. Like you can add some bounds, variable bounds to the Tij, right? And the leader's problem focus on setting tolls for each edge such that the leader can maximize the total revenue of all the highways. Okay. So now what will be the follower's problem, right? So remember the follower is solving for a different problem, right? The objective is different than the leader's problem. The follower is minimizing the total travel cost, right? So if it will be a sum over all the path from origin to destination, and then for each of the edge, the ij in the path, we need to consider, the base cost plus the toll, right? So this is essentially the total cost of the travelers traveling from the origin to destination. And then we need to have some constraints on demand satisfaction. So if you sum over all the paths, they have to satisfy the total demand, right? That will be the total number of travelers who wants to travel from origin to destination. Okay, and you can perhaps set some bounds on those variables, right? For example, you cannot make each path too congested. There will be an upper bound on XP. Right? So that then, the travelers will react optimally. Okay, so let's put this together. How does this bilevel optimization problem look like? Right? So if you have one single toll setting agency, then the agency is optimizing the total profit But then when you're optimizing this problem, you don't know what is the optimal response of the travelers, right? So then we have to add some constraints to the traveler's path, right? So essentially, this is a constraint you add to the leader's problem, right? So there is an optimization problem embedded in another optimization problem, right? So you have to use those XPs such that they minimize this optimization problem, okay? So again, here in the leader's problem, we are optimizing the toes, and then we have to calculate the objective based on the optimal response of the followers. So what are the optimal response of the follower? It is the optimal solution of a different optimization problem, right? So these optimization problems are served as constraints in the maximization problem, right? It's very similar to the first problem, right? When the leader decides how much quantity they want to produce, they have to make sure that they are aware the follower will respond optimally to whatever decisions they make. Okay. Yeah. Let's pause here a little bit to see if there are any questions. Yes.
Is like the sub-minimization problem the same as the best response function as from the previous example?
Yeah, exactly. So in the previous example, the best response function has a closed form solution, right? So then you can just plug it into the original problem. But here, the minimization of, let's say this is a kind of like a linear programs, right? It is less trivial than the previous example. So you have to write it as generically as an optimization problem embedded in another optimization problem. And you are right in the sense that this is like the best response function, right? If you can get this optimization problem in closed form, that's the best response function, basically.
And it would be a function of t in this case.
Yeah, exactly, yeah. Right, so this is essentially like given the toe, then the follower will respond optimal to the t. Yeah. Any other questions? Here.
Can there be a case where the travelers might not respond optimally, like based on sentiments and so on?
Yeah, so that's a good point. So here we just make an assumption that all the travelers are rational in some sense. Okay, but of course in practice, not all the travelers are rational. Right? And then they have different preference. That's a more complicated problem. Yeah. Okay, so let's generalize this little bit to what is a mathematical formulation of a bi-level optimization problem. Okay, so here we have two sets of problems, an upper level problem and a lower level problem. Okay, so here if you just look at this objective and this constraint here, right? So this is essentially the leader's problem, right? But besides the constraints of the leader, so to start with, X are the decisions of the leader and Y are the decisions of the follower. Okay, so the leader, so why do I will explain that in a second, why do I put a Y here as well? So you can just assume the leader is minimizing over X, okay? So the leader is minimizing over X while anticipating that the lower level problem will be solved to optimality, right? So this set X is like the best response function. So this set S of X will return the best response of the follower for any given X, right? So for any given leader's decision X, this set S of X will contain all the optimal solution of the lower level problem. Okay, so this set is called a rational reaction set. Okay, so rational reaction set is defined as follows. For given X, this set will represent the Y's that optimizes the follower's problem. Okay, and y has to be in this best response set. Okay. So as you can imagine, if the best response is unique, as in the first problem, right? In the production problem, the best response is unique. We don't need to optimize for y here, right? But if the best response is not unique, then there are some distinctions related to how do you classify the bilevel optimization problem. Okay, yeah. So let's talk about that when this best response is not unique. Okay. So let's look at this toe setting problem. Okay. So supposedly, I set the toe, the leader set the toe in the following way, right? So the toes for the A and B are 2 and 2, for C and D are 3 and 4. Okay. So now if you add them up, right? Let's do some very simple calculation. The total cost of traveling through A and B is 19, and the total cost of traveling through C and D is also 19, right? So in this case, the best response set is not unique, right? So if you travel through A and B or C and D, it's equivalent for the follower, right? But it's not equivalent for the leader, because if you travel through A and B, the tolls are lower than traveling through C and D, right? So the leader will make different amount of money based on the traveler's decision. Okay, so that's a distinction of a so-called optimistic bilevel optimization versus pessimistic bilevel optimization. By optimistic, we define that the follower will always make the decision that is best for the leader if these two solutions are equivalent. Okay, so here if you travel through A and B and C and D, it's equivalent for the follower, right? But to align well with the leader's objective, we assume that the follower will always choose route CD, right? Because if the follower chooses route CD, then the leader will make more money, right? So that is so-called optimistic bilevel optimization problem, right? So when multiple responses are optimal, the follower takes the decision that works best for the leader, right? So the pessimistic means that when multiple decisions are optimal, the follower takes the decision that works worse for the leader, right? In practice, usually people do somewhere in between, right? If you travel through a route, you don't really care about how much the toll setting agencies are made, right? You wouldn't, pay more tolls just to make the toll setting agency happy, right? But mathematically, usually we deal with optimistic setting. Okay, so the follower usually align their objective with the leader if they can. Right? So, yes.
How can multiple responses be optimal? How does that come about?
Yeah, so like this example, right? You have multiple optimal solutions to the follower's problem, right?
Okay.
Like when the tolls are set, these two solutions will give the same cost to the follower, right? So essentially, this is saying that this set S of X is not a singleton, right? For most optimization problems, when you solve the optimization problem, there is a unique solution. But sometimes when you solve an optimization problem, the solution is non-unique, right? So in case of linear programming, as you can imagine, when the cost vector is vertical to a face of the polyhedral, right? Then usually the optimal solution is obtained at an extreme point. But there are some cases when the cost is vertical to a face. This entire face is optimal. Right? That's just one case of the solution being degenerate. Okay. So here's just a very trivial example where you have two optimal solutions, right? And then the follower will have some freedom to choose. But in optimistic case, we just assume the follower will choose the solution works best for the leader. Okay, yeah. Any other questions here? So here, so that explains why we are also minimizing the y variables here. Right? So if this y is s of x is a singleton for any x, you don't need to optimize y in the leader's problem. Right? So in the leader's problem, if you assume the response is optimistic for you, then they have to optimize both x and y in the upper level problem. Okay. Yeah. So this is the most commonly used framework in bilevel optimization. I don't know this is more practical than the pessimistic case, but this is easier to solve than the pessimistic case. Perhaps that's why people pick this case, right? And then now I will show you the pessimistic formulation. You can easily see that it is much harder to solve than the optimistic case, right? So here it's saying that when the leader minimizes over x, then the follower will pick the solution among this best response set that maximize this function, right? Pick the best response, will make it the worst case for the leader. So there's sort of like a min-max type of formulation here, right? So actually this SX set itself already involves an optimization problem. And then you are adding another level of difficulty by saying that I'm going to pick the worst response by maximizing Y in this best response set. Okay. Yeah. Yes.
So how is maximizing Y pessimistic?
Yeah, so since, if you are the leader, they are trying to minimize this function f, x, or y, right? And then the follower can choose any response from this rational reaction set as of x, right? But then if you are choosing the one, let's say, that minimize this function f of x, then the mean and the mean are aligned, right? So if you pick y in set s of x, then this is essentially minimizing x and then minimize over y, right? But if you're saying that, I'm going to pick the one y that maximize this function, right? That would be the worst for the leader. Okay, yeah. Yeah, and this is much more challenging to solve than the optimistic formulation. So we won't talk about how to solve the pessimistic formulation in this class. Okay, so just real quickly, how do we solve the bilevel optimization problem? So one of the ways to solve the bilevel optimization problem, so here again, I'm only going to talk about the optimistic formulation, right? So you have a minimize x over x and y here in the upper level, and y is an element in the rational reaction set. Okay. So first of all, this can be reformulated as a single level problem. Right? We do know how to solve single level optimization problem. So the nastiest thing here in this formulation is this set here, right? This rational reaction set that involves an optimization problem. The rest of the problem are just what we have encountered before. So if we can characterize this set, then you can kind of reformulate it as a single level problem. So let's first define a value function of the follower problem. So we have talked about value function before in previous lecture. Basically, it is a function related to an optimization problem. Right? So let's define phi of x. So basically, phi of x is minimizing the follower's objective for a given leader's decision. Right? So this is a function describing the best objective value of the follower given the leader's decision is x. Right? So this function involves solving an optimization problem. So this is called a value function of an optimization problem. So the x is like the parameter in this optimization problem. Right? Once you give an x, the leader's decision, then the followers solve the optimization problem to optimize their profit or minimize their cost. Okay. So if, let's say for the sake of the argument, if you have this best response function in a closed form, which we did for the production problem, right? Remember we were able to calculate the best response of the follower in the production problem, right? Just set the derivative to 0, then you have a closed form solution, right? So if you can do that, then we can reformulate this problem as a single level problem in the following sense, right? So you have constraints of the leader's problem, constraints of the follower's problem, and also the objective value of the follower's problem has to be less than or equal to phi x in order for this response to be optimal. Okay, so this is a subtle point here, right? So recall that phi x describes the optimal value of the follower's problem for a given x. So the set S of x, I'm going to make a claim that the rational set S of x is nothing but for all the y's. First, y has to be feasible. Second, y has to be optimal. What does it mean for y to be optimal? Since I know for a given x, the optimal solution for this problem is phi x. If I only choose all the f x of y that are less than or equal to phi x, then those y's must be the optimal ones. Actually, they should be equal, right? So all the y's that equals to the optimal objective are the optimal y's, right? So first they satisfy the constraints, right? So in order for a variable y to be optimal, basically we check two things. One is that they are feasible. Second thing, they are optimal, right? So this constraint guarantee the y's are optimal. And since I know what are the optimal objective, if I pick the y's that are lower than or equal to the optimal objective, then those y's must be optimal. Right? So if you add these two things together, that describes the rational reaction set. Right? So that's why we can just plug in these two constraints here. Then for all the y's that satisfy those two constraints, they must belong to the optimal reaction set. Okay. This is a very subtle point here. Okay. So with that, we can replace the bilevel optimization problem with a single level optimization problem. Right? There are no embedded optimization problem here. You just minimize x and y altogether. Okay. Yeah. Of course, the difficulty here is that it is very hard to get this value function, right? So for the production problem, it has a closed form solution, but imagine this, let's say this lower level problem is an MLP, right? Then how to get the value function of an MLP, it is a super difficult problem, right? It's even harder than solving a single instance of an MLP, right? So think about you want to get the optimal value of the MLP for a whole set of x, right? So that's a very challenging problem. So in general, this approach won't work unless you have a very simple problem, then you have a closed form description of the value function. Okay. Yeah, so another more commonly used approach is to do a reformulation based on optimality conditions. Okay, so the idea is that we can replace y belong to the optimal response set through the optimality condition of the lower level problem. Okay, so just a refresh of your memory, what optimality condition have we covered so far, right? So for linear programming problem, we covered two optimality, very nicely used optimality condition, right? If you have primal feasibility, dual feasibility, and the primal and dual objective are equal, then you basically, this is a strong duality optimality condition. And then we can also use the KKT condition. Right? If you forgot that, take a look at the linear programming lecture. We did prove that these two conditions are equivalent to each other. Right? So you basically have primal feasibility, dual feasibility, and complementary slackness is equivalent to the primal and dual objective are equal. And then for convex NLPs, we have a KKT condition, right? If you assume you satisfy some constraint qualification like Slater's condition, then basically we have a primal dual feasibility, complementary slackness, and stationarity, right? So you can replace a lower level problem with this type of optimality conditions to reformulate the problem as a single level problem. So let's consider a very simple case, actually the simplest case of bilevel problem, which is we call LP. The upper level problem is an LP, the lower level problem is also an LP. Right? Then what we have is that let's assume the first level problem is related to the x variable, then the lower level related to the y variable. These linear constraints are the constraints on the upper level, and the lower level has to solve this particular linear programming problem, which are the best response of the follower, right? And then since this is a linear programming problem with respect to y, you can replace this linear programming problem with its optimality condition, right? So for all the y bar that optimize this problem, they must satisfy let's say the KKT conditions of this linear programming problem, right? So the KKT conditions are let's say dual feasibility for this problem, the primal feasibility for the problem, and complementarity conditions. Right? So now you replace this very nasty constraint with the optimality condition of the lower level optimization problem. Right? So for all the y that solves the lower level problem, for all the y that are the rational reaction set, they must satisfy these three constraints, right? And then this condition is both necessary and sufficient, right? So that's why you can replace the lower level with these three equations. Okay. Yeah. So all the rest of this lecture will based on optimality condition. And let's pause here to see if people have any questions. Yeah.
I'm sorry, so what does y bar refer to here? How is that any different from y?
Oh, okay, yeah. So let's just, this is a subtle point, right? So here, let's say y bar is a variable related to this inner problem. So y bar optimize this problem. You can think about y bar as equivalent to y, but I just want to use a different notation to represent, y bar is the optimal solution of this subproblem. Then all the y bar that optimize this problem forms this set, right? And then y has to be in this set, right? But you can use the same notation as y here.
And so all those y bar satisfy those three KKT conditions?
Yeah, so all the y bar has to satisfy those three KKT conditions. Then since y is in this set, then you can just say y has to satisfy those conditions.
And they satisfy them for any x that we choose?
Yeah, exactly.
Okay.
Yeah. Okay. Other questions here? Yeah. All right. Then you can just replace this constraint with these three constraints to solve a single level problem, right? And similarly for a convex lower level problem, right? So if you assume this particular problem with respect to y is a convex nonlinear programming problem, then you can also use the KKT conditions, right? Since KKT conditions will be necessary and sufficient if you assume, let's say, Slater's condition hold for the lower level problem. Okay, now we can reformulate that using the KKT reformulation. This is stationarity, this is primal feasibility, then we have dual feasibility, and then the complementary slackness, right? So you can write down the stationarity condition in terms of the f and g functions. Okay. So this seems to be nice, but what are the difficulty of KT reformulation? The main thing is that is because this nasty complementary slackness, right? So it creates some bilinear term even for the linear programming problem. Okay, so let's go back a little. If you look at the linear programming problem, the primal and dual feasibility are linear, right? The linear constraints are easy, but here we have the lambda times x and y, right? So lambda is the dual variable, x and y are primal variables. Then you have a bilinear term which is non-convex, right? So that's a difficulty of the KKT reformulation. So in the literature, this type of problem are called mathematical program with complementarity constraint. Basically, you have two variables, x times y, and x times y has to be equal to 0. Okay, so you can think about x and y as complementary to each other. So in the literature, you will find people call this type of problem MPCC. Some people call it MPAC, math programs with equilibrium constraints, right? So this is a very active research area in so-called non-smooth optimization. So there are some tailored techniques to solve those problems with complementary constraints. We are not going to the details of non-smooth optimization and complementarity constraints. So we'll just talk about two very naive approach to deal with complementarity constraints. One of the naive approach is that let's just use a global solver. Right? So now if you have an LP, you have bilinear term, not a big problem. You use a solver like Groovy, it will handle those bilinear terms for you. Right? Use McCormick envelope for SDP relaxations and so forth. But of course, using a global solver can be very expensive. Right? You have to do things like spatial branch and bound on those bilinear terms. Right? And another very naive approach is to reformulate this complementarity condition using big M type of constraints. Okay, so if you have these two terms, right? G of x times lambda I equals to 0. This is like a complementary constraints in convex optimization. And now you can introduce a big M parameter here. Basically it says either this function is 0 or lambda is 0, right? So we have a z variable to denote which one is 0, right? So if zi is 0 here, it will force gi of x to 0. And if zi is 1 here, it will force lambda I to 0, right? So that this big M type of constraint will give you the complementary conditions. But of course, now you need to be very careful in choosing the big M parameter on both this primal constraint as well as the dual variables here, right? But for a linear program, you do know how to bound them, right? For a linear program, you can take the dual by yourself and check what will be the bounds of the dual variable. For a convex problem, it's less straightforward. Perhaps you have to use some intuition to derive the bounds for the dual. Okay. Yeah, but the thing with this formulation is that, let's say if Gn of x is a linear function, then this is an MILP, right? Then you can use your MILP solver to solve this type of problem. Okay. Any questions here? Yeah, so now let's just write it down. You can apply your MILP formulation to an LP bilevel problem, right? This will yield some constraints with big M parameters. And there's another type of reformulation, very similar to the KKT reformulation, is you can use the strong duality condition rather than using the KKT conditions, right? So instead of using the complementarity condition, you can enforce this constraint, right? This is basically says the objective of the this primal problem equal to the objective of the dual problem, right? There is nothing fancy here. You just take the dual of this LP with respect to the y variables here. Then you get this is a dual objective. Right? But the thing is that you cannot avoid having some bilinear terms. Right? Here you have some this x transpose lambda. You have some product of the x and lambda variables. We cannot really avoid having some bilinear constraints. Let's see. Yeah, so those are the the lower level with LP, or the lower level is convex. You can use reformulation. But what if the lower level has integer variables? Then you cannot use any optimality conditions, right? There are no strong duality result for integer programs. So this problem is still a very active research area. That's why we are not talking about that. I will show you a reference at the end of this lecture. If you are curious, you can take a look. As you can imagine, typically those variables will involve some branch and bound cutting planes in order to solve those lower level integer problem to optimality. Okay. So let's pause here before I talk about a related topic. Any questions here? Yes.
On just the previous slide.
Yeah.
Why is the constraint that the dual objective is greater than the primal problem? I guess maybe I'm just missing something.
Oh, okay, yeah. So you can set them to be equal. There's then nothing wrong with that, because usually, if you are minimizing, then the dual will give you a lower bound of the primal, right? You can prove that. The dual feasible solution, any primal dual feasible solution pairs, the dual objective always give you a lower bound of the primal. If you set them to be less than equal to, then they are equal, right?
Okay.
We only need one side of, but you can set them as equal as well. It doesn't matter, yeah. Okay. Any other questions? Yeah, very good catch. Yeah, so now let's talk about a slightly related topic with bilevel optimization. It is called robust optimization. So this can be seen as a special case of bilevel optimization. I will show you how it is related to bilevel optimization in the next slide. But first of all, I want to make some connections of robust optimization with two-stage stochastic programming. Okay, so in two-stage stochastic programming, remember that we are optimizing for the expected cost. Right? So the news vendor is trying to optimize his or her expected profit by selling the newspapers. Okay, so in stochastic programming, we are taking a so-called risk-neutral perspective, right? We're minimizing the expectation. But in robust optimization, it is a so-called risk-averse approach. I'm optimizing for the worst-case scenario. Okay, yeah. So this is commonly used in some areas as well, where if you are very conservative in decision making, you can use robust optimization. Actually, you can use those philosophies in your life decisions as well, whether you are a risk neutral person or you are a risk averse person, right? So I would prefer to use stochastic programming in my life decision, optimize for the expected value rather than the worst case. Okay. Yeah, so here, the other difference here is that in robust optimization, you don't need a probability distribution. Right? So in stochastic programming, we are optimizing for the expected value. To calculate the expectation, you need a probability distribution, right? Either uniform or Gaussian distribution and so forth. But in robust optimization, you are just picking the worst case scenario. You don't care about the distribution of those parameters. Right? So that's why typically we are not talking about probability distributions. We are talking about something called uncertainty set. So let's show a simple formulation of robust optimization. Okay. So this is the simplest form of robust optimization where we have linear objective, linear constraint. It is a robust linear programming problem. Okay, so you are optimizing a variable x, right? And the x is, the problem is a linear function of x subject to linear constraints with respect to x, right? But then let's assume those parameters c, a, and b are not deterministic, right? So they live in a so-called uncertainty set. Okay, so you those are the uncertainty set. So what we are doing here is basically assuming the C, A, and B belongs to a given uncertainty set, right? So this uncertainty set can be a polyhedral set of C, A, and B, or an ellipsoid set, right? For example, if you have let's say let's draw an example in 2D, right? So in a deterministic problem, if you have two cost coefficients, then they are deterministic. It's just a point in this 2D plane, right? So in a deterministic problem, those parameters are deterministic. But in robust optimization, you assume you don't know exactly what the cost would be. You just assume, for example, it can be, let's say, so let's say, for example, you assume that the C can be any value within this rectangle. Okay, so this is your set U sub C. Okay, and then you are choosing the C that gives you the worst cost. Okay, so that's why I say you have a maximization problem here, which after you determine the X, the cost will be the worst case over this rectangle. Right? An uncertainty set can be any, let's say, continuous set, right? You can think about in high dimension, you have a hyperrectangle, or you have a high dimensional circle or an ellipsoid. That are the uncertainty set people usually use. Okay, and similarly for those cost coefficients, not cost for those constraints, right? So if you have, let's say, deterministic problem, each of these constraints, AI, so AI transpose X less than or equal to BI are a particular linear constraint, right? If you are solving a deterministic problem, you just have, M constraints in a linear programming problem. But in robust optimization, you don't know what those coefficients are in your constraints. You assume they live in an uncertainty set. Right? So for all the A's and the B's in a continuous uncertainty set, those constraints must hold. Okay. Yeah. So that's why I say we are optimizing for the worst case scenario, right? So you can think about this as a leader or follower game as well. The leader is choosing a given vector X, the decision you want to make now, right? And the follower is giving you the worst case parameters you can get. Okay. So you can think about the follower as things like nature, right? If you are investing in something and nature is giving you the worst case outcome you can get within an uncertainty set, right? So you, in some of the problem like infrastructure planning, right, you do want to consider the worst case. Let's say if there is a thunderstorm, that could be the worst case parameter you can get from nature, right? But your infrastructure plan should be robust to all the potential extreme weather. That's when robust optimization is used. Okay. Yeah. So now maybe a quick question here is that, maybe I will ask in the next slide. So first of all, there is a very quick reformulation of the problem to get rid of the min-max. Okay. As you can see here, we are picking the C that maximize the objective, right? So this is equivalent to say that the the objective, let's denote the objective as alpha here. Alpha has to be greater than or equal to C transpose X for all the C in this uncertainty set you see. Right? You have seen this formulation before when we are adding those OA cuts. Right? You have an objective, you have an alpha to represent the objective, and then the alpha has to be greater than or equal to all the C in this uncertainty set. Okay. Yeah, so this is an equivalent formulation to the robust optimization problem. So now why I say robust optimization is a special case of bilevel optimization. And the reason is that with this simple reformulation, you can get a single level problem. Right? Since the min-max are optimizing the same objective, you can use this reformulation here. All right. So let me ask the following: if we do this reformulation, are we done yet? Right? Because the only difference with respect to the regular optimization problem is that those constraints are defined on a continuous set. Right? So this UC can be a hyperrectangle. Right? So you have an infinite number of constraints here in this problem, because the C in the previous slide, it is defined on this continuous set, right? The C can take any points within this set, right? So in other words, there will be an infinite number of constraints in this problem, but the number of variables are finite, right? You only X and alpha are finite dimension variables, okay? So again, when you have a problem with infinite number of constraints, but a finite number of variables, this is so-called a semi-infinite programming problem. Okay, why is semi? Because the variables are finite, the constraints are infinite, right? So how do we solve this semi-infinite programming problem? There are some duality-based formulation. For example, as you can see, there is a min-max problem. You can try to take the dual of the max problem to solve that. Here we will show you another much simpler way of solving this problem, at least simpler in understanding the algorithm. Okay. And the intuition is quite clear, because we have done this multiple times, right? When you have a problem with a very large number of constraints, like what we did in, for example, Lagrangian master problem or Bender's reformulation, right? We do have a finite number of constraints, but we don't want to use all those constraints. Right? There can be combinatorially many number of constraints. This problem is even worse, right? The number of constraints is not even finite. It's like infinite number of constraints in this problem, right? So how do we solve this type of problem? To use the intuition we had before. I recall that what we did in Bender's reformulation is that when we solve the Bender's master problem with a small number of Bender's cuts, right? Then we fix the solution and find the cut that are most violated, right? Then we add that cut back to the master problem, resolve again until no cuts are violated, then we converge, right? Can we adopt a similar philosophy to this problem, right? The difference is that this problem has an infinite number of constraints. So how we are going to do that? We will use a similar idea in those cutting plane method. So let's start with, let's call this problem the master problem, where we start with a finite number of constraints. You can think about those set UC superscript k, UAIK, UBIK as a finite set, rather than a continuous set, right? Well, for example, in this rectangle set, you can just take a few arbitrary points in this hyperrectangle set, right? Then you have a finite number of constraints, right? So then we solve this problem, right? Now the problem has a finite number of variables and constraints. Then let's assume the solution to this problem is xk and alpha k. Now the next step is we find the most violated constraints for xk and alpha k. How do we do that? You can just solve this simple optimization problem. Right? If we do, for for example, let's check these constraints Cx, C transpose X less than or equal to alpha. Now we fix xk and alpha k, and then we find the vector C that belongs to the set UC to maximize this constraint, right? Then you basically are finding the maximum violation of the constraint. And if this UC set is a convex set, then this is a convex problem, right? Yeah. Linear objective with convex constraint. And then the other thing you can do is that for each of the constraint, we also find the max violation of the constraints. So if you find none of those constraints are violated in the sense that this thing is less than or equal to 0, then meaning that even the most violated constraints are not violated, then you can terminate. Right? For a polyhedral set, you can terminate in a finite number of steps. For a convex nonlinear type of set, at least you can get something like finite epsilon convergence. Okay, so that's the idea. We have been using the similar ideas multiple times, right? In Benders, in Lagrangian, and so forth. This is just an application of these cutting plane methods to a semi-infinite programming problem. Yeah.
How can a finite number of constraints though describe the infinite number?
Yeah. Yeah.
Within the set?
That's a good point. Actually, as I said, if you have let's say a nonlinear set, usually you can think about, for example, if you have a polyhedral set, I believe you can prove that if you enforce the constraint on all the extreme points, then you are done. Right, so you can take the convex combination of those constraints, and then you find out that they will infer all the constraints you have.
So you only take, I guess, in this case, like the cost, for example, at the extreme point.
Yeah, exactly. You can try to prove that. Maybe we can leave this as a homework problem. If you have a polyhedral set, bounded polyhedral set, just take those extreme points, then you are done. You don't need any other points. For a non-polyhedral set, maybe you cannot. I believe you cannot approximate that with finite number of constraints. But you can set a tolerance. Let's say my max violation of the constraint is epsilon being like 10 raised to the power of -5. Then you can terminate in a finite number of steps. Right? It's just like you are adding some sort of outer approximation cuts to this set. Yeah. Well, that's a good intuition. Yeah. Any other questions here? Okay. Yeah. So most of my notes follow from these notes here. It's called a gentle and incomplete introduction to bilevel optimization. The authors are very humble. Yeah. So they have some more advanced topic in this note as well. And in this textbook, actually, there is another topic called flexibility analysis, where chemical engineers like Grossman invented in the 70s. Some of those work actually predates what people did in robust optimization. So this is called, if you read the chemical engineering literatures, you'll probably see things called flexibility analysis. Okay. So those flexibility and not feasibility analysis, flexibility. Right. So some of those work and algorithm predates what people did in robust optimization. Of course, as a chemical engineer, I'm very proud of what my advisor did. So you can take a look at those literature as well. Okay.